Okay guys, in this video we're going to introduce redox reactions and how they work as part of our redox and electrochemistry unit. So here we go. So first of all, redox. Okay, redox is actually a shortened word that we use that stands for something a little bit bigger. All right. So when we say we have a redox reaction, what we're really saying is that we have an oxidation reduction reaction process. Okay, so that doesn't mean much to you guys yet. But if we take a look at it, and we'll break it down into what does it mean to be an oxidation reduction reaction. So first of all, anytime you have an oxidation or a reduction going on in a chemical reaction, we're talking about electron transfer. Okay, so we're not really looking as much at what has happened to the individual bonds or the compounds formed, but we're now tracking electrons movement in more detail. Okay, so we're focusing on where do the electrons go. Okay, now, in a redox reaction, we always need to have at least one thing that is gaining electrons and one thing that is losing electrons. Okay, so it comes as a pair. So one thing, gains some electrons, one loses it, or one thing gets reduced and one thing gets oxidized. So we're going to use the terms reduction and oxidation to indicate the movement of electrons. All right. Now, when we have something that is being gaining, okay, so when you gain electrons, we call that a reduction. Okay. When you lose electrons, we call that an oxidation. All right. So that's kind of how we talk about things. So anytime we say, hey, that is being reduced, that means it got some electrons. Or, oh, that was oxidized, that means it lost some electrons. Okay. If we take a look at some of our traditional definitions for reaction types, like combination, decomposition, single displacement, and combustion, these reaction types are all redox reactions. Okay, so we didn't identify that in previous units, but now looking back, in all those reaction types, to get them to form new bonds and switch partners and do what they do, there has to be a movement of electrons, which causes an oxidation reduction process to happen. Okay, so because they have a shift of electrons, these are redox reactions. Now, typically, a double displacement reaction is not redox. Okay, so of the 5 types we talked about, double displacement is not a redox reaction. Okay, and if we look at what's going on with double displacement, while double displacement focuses on switching partners, so if we remember double displacement, your cations and your anions trade partners, and they get new partners. And the key to our double displacement, remember, is that one of your new compounds will be a precipitate, or a gas, or a liquid. Okay, in all those cases, the reaction for double displacement happens because we're creating something that leaves solution, okay, as a gas, a liquid, or a precipitate. Now, also, one of the things that we talked about in double displacement was that we could assume that the ionic charge for the reactants was going to be equal to the ionic charge for the products. Okay, that was one of the little rules that we set up for double displacement. We would often say, well, what if we have iron 2+? How do we know as a product it's still iron 2+? And I said, well, we're going to assume it stays iron 2+. And the reason why we can make that assumption is that under typical conditions, double displacement don't transfer electrons; they just switch partners. Okay, so they're not a redox because there is no transfer of electrons in the shape of one thing losing something and one gaining them. They just find new partners. That's all they do. Okay, so that's kind of the overview of what redox is. So let's go a little bit more detail on it. Okay, so first of all, reviewing this idea, what's it mean to be oxidized? So if you're losing electrons, you are oxidized. Okay, sometimes we say that like iron gets oxidized to make rust. Well, that process, iron metal loses electrons to form iron oxide. Okay. Traditionally, that definition was all about gaining oxygen. So traditionally, when we first started defining this, when you were losing electrons, the most common thing that you would bond with was oxygen, okay, like in the rusting process for iron. So that's where the word oxidation comes from, is that most of the early chemistry saw compounds like metals combining with oxygen, and there's a certain chemistry that came with that. So we call that getting oxidized. Once we know more about electrons, we realize, oh, what's happening here is they're gaining electrons, they're losing electrons in a process, and essentially they're losing them because oxygen's taking them. Okay, so because they're losing electrons, we still use the term oxidation. Okay, other things we could talk about is losing electrons, or also the increase in the oxidation number. Okay, we will take a look at oxidation numbers shortly, but for right now, just kind of realize that one way you can track the losing of electrons is to look at actual specific numerical values associated with elements, and they're called oxidation numbers. Okay. Now, one side note, not really a side note, but part of this thing too, is that if you are getting oxidized or you are undergoing oxidation, that means you must be a reducing agent. Okay. So if you are losing electrons, that means you are giving them to somebody else, or you're causing something else to get reduced. All right. So if you are being oxidized, that means you're the reducing agent in this process. Okay, so you kind of look at it from two different perspectives. If you're oxidized, you're reducing something else, which also means that if you're getting reduced, you must be oxidizing something else. Okay, which brings us to our next slide on reduction. Okay, so anytime you gain electrons, we call that being reduced. Okay, that again comes from the idea of oxygen originally. So being reduced, you're reducing the amount of oxygen on something. So if you take oxygen away from something, that was our traditional definition. Now we talk more about the movement of electrons. So when you gain electrons, okay, you're being reduced, which would also correlate to a decrease in this oxidation number, or this numerical value assigned to your number of electrons. All right. Same token, if you're getting reduced, then you are the oxidizing agent, which means you are causing something else to be oxidized in the chemistry that goes on. All right. Now, these two things can be a little bit confusing. Which one is which? How's it go? So we have a really good acronym that really works out. It's really easy. We say that Leo Goes Ger. Okay. So anytime you try to think about, okay, what's going on here, oxidizing, reducing, what's happening, what's going on, think about Leo Goes Ger. Okay. So Leo Goes Ger: lose electrons, oxidized, gain electrons, reduced. Okay, it's pretty simple to remember. Leo the lion, sometimes they say Leo the lion goes Ger, but I just go Leo goes Ger. And in my head, you'll watch me as we talk about this unit. If you talk about something, I'll go Leo goes Ger, because I actually sometimes still need to work it out in my head even too. So anytime you lose electrons or oxidize, that's our Leo, and gaining electrons is reduced is our Ger. Okay, so Leo Goes Ger is the way that we can keep track of all this stuff. There's other ones too. There's like one they call Elmo, people say. So if you say the word Elmo, losing electrons means oxidized. So losing electrons means oxidized. That's another one. Another one I've heard of is oil rig. Like oxidized is losing, rig for reducing is gaining. I don't know. There are different acronyms. This is the one that sticks in my head the best, is Leo Goes Ger. Okay. So if we look at a chemical reaction like we see on the screen, where we have magnesium reacting with chlorine to make magnesium chloride, first of all, we know this is a combination reaction, which means it's going to be a redox reaction, because all combination reactions are redox reactions, which means that the magnesium and the chlorine, one of them is being oxidized, one of them is being reduced. Okay. Now, written like this, it's sometimes not as easy or obvious to see which one's being reduced, which one's being oxidized. So we want to break it down a little bit more detail to figure that out. Starting off with the full reaction, again, not a lot of great information here. It's balanced, it's ready to go. What we want to do is start by running the ionic reaction. Okay, so earlier in the year we called it a net ionic reaction. So we want to get the things that are actually making changes here, and we want to get rid of our spectators. Because spectators that are there, that's fine, but they're not being oxidized, they're not being reduced, they're just spectating, okay? So we want to get rid of our spectators so we see what's really happening in terms of the chemistry. So in this case, magnesium is combining with chlorine as a diatomic. We're getting magnesium ions as a 2+, and we're getting chlorine ions as a 1-. So we have two of these chlorine ions is a 1-. And we assume that this is solution here. It should be noted, but it should be in solution, okay? Which means that we now have magnesium. It started off as neutral, and it went to being a 2+, okay? So if you were magnesium that's neutral, it has 12 electrons in it. It went to being a 2+. Well, being a 2+ means it's lost 2 electrons, right? It now has 10 electrons in it. So the magnesium is our reducing agent, okay? So magnesium got ionized, it got oxidized. It went from magnesium to magnesium 2+, and it gave away 2 electrons, okay? So this is the oxidation part of this process. So magnesium was oxidized. The chlorine went from being neutral to being a charge. So it gained electrons, okay? Now each chlorine gained 1 electron, but a total of 2. So the chlorines gained electrons here because they went from neutral, okay? So chlorine had, what's chlorine? 17 electrons. To each chlorine now has 18 electrons. So it gained 1 electron, so it was reduced, okay? Meaning it was the oxidizing agent, okay? Now, what we call this are redox half reactions. and it's pretty common in the chemistry world for redox, is to take a reaction and split it into two halves or look at them independently. So we say what is going on in terms of oxidation, what is going on in terms of reduction, and we look at them as individual parts of the chemistry. So this part is losing electrons, here we are gaining electrons, so we have oxidation and we have reduction. Okay? Let's do another example on the board. So up here I have aluminum plus lead nitrate making aluminum nitrate and lead. Okay, a classic single displacement reaction that we've done, probably hundreds of these so far this year. And our first step is let's break this down into a net ionic so we can kind of see what's a spectator and what is doing the chemistry. So we have our aluminum plus lead nitrate. Now if this is in solution, that means we actually have lead ions as a 2+, and we have 2 nitrate ions as a 1-. Okay? They're going to make aluminum nitrate, and this will be in solution, because we know all nitrates are in solution, which means we have aluminum as a 3+, it takes 3 of these to balance, plus we have nitrate as a 1-, and then we have some lead. Okay? So at first glance, it looks like, okay, we have aluminum, we have our lead, our nitrate. Everything is, we're not really balanced completely here. So if we want to balance this chemical equation, we take a look and over here, we have 3 nitrates. And here we only had 2. Okay? So going up to balancing our equation, we need to have a 3 here. We need to have a 2 here, which means there's a 3 here, which means there is a 2 out here. Okay? So we want to balance it, which changes things down here slightly too. So our aluminums become a 2, our lead becomes a 3. We have 3 times 2 now, so we have 6 nitrates. We have 2 aluminums. We have 3 times 2 for 6 nitrates, and we have our 3 leads. Okay? Now we have our balance equation. And if we start to break this down, well, let's see what's happening. Aluminum is going from aluminum to aluminum 3+. Lead 2+ is going to lead neutral. 6 nitrates -1 are turning into 6 nitrates -1. So this part of the reaction is not making any changes. Okay? So it's not being oxidized, it's not being reduced, it's a spectator. So we're going to get rid of that in terms of our half reactions. It's there, it's providing charge balance, but it's not reacting, okay? Which means what we really have is we have 2 aluminums reacting with 3 leads, and we're making 2 aluminum ions and 3 lead atoms, neutral, okay? So let's now look at our half reactions here, okay? So we have 2 aluminums and 2 aluminums, which means your 2 aluminums as neutral is turning into 2 aluminums with a 3+ charge. Okay? So each aluminum has given up 3 electrons, or for a total of 6. So it has given up 6 electrons. So in this case, aluminum is going from neutral to positive. That means it has lost electrons. So if it has lost electrons, it's LEO, and losing electrons means it is oxidized. So aluminum here is oxidized. Okay? The lead, we have 3 leads, and we're going to have to add in 6 electrons to make, 3 leads that have a 2+ charge. 3 leads that are neutral, okay? So 3 leads with a 2+ charge, give them 6 electrons, so we have 2 times 3, then you'll end up having 3 leads that are neutral, okay? So in this case, is our Ger, so our lead is reduced in this process, okay? So that's kind of how you break it down. Okay, I'd probably put in more steps than maybe you need to see that or visualize it. But really, the first thing you want to do, if you have like single displacement or anything, is get rid of your spectators. Okay, because they're not oxidizing, they're not being reduced. Take a look at the net ionic. and then do your 2 half reactions to identify what's going on. So in this case, the aluminum, because it becomes positive, that means it's going to lose these 6 electrons, so it was oxidized. The lead, because it comes from being positive to neutral, that means it's gaining electrons, right? It's gaining negative charge to balance that out. It's being reduced here, okay? Okay, we'll have more practice with this for you guys to do as we move forward.